My name is Alexi Reed, and I'm the co-TA for Pod 1, the introductory R pod, and today I'll be showing you how to create a regression coefficient forest plot like this one. For my research, I do a bunch of regressions, and whenever I have to do a poster or oral presentation, it annoys me only having a table to put in to show my results. So I decided that whenever possible, I would try to use a forest plot like this to more clearly and efficiently communicate my regression results, especially for presentations where interactions with other conference attendees may be brief, but they want the results at a quick glance, like a poster. So to orient you with this plot, we have the coefficient estimate on the x-axis and then all the predictor variables on the y-axis. Each dot here represents the actual coefficient estimate from the regression, while the bars are the confidence interval for each coefficient. If the confidence interval crosses this zero dashed line, then it proves to not be significant in our regression and is gray. If the coefficient was significant and therefore not crossing zero like this, then it was maroon or red. First, you want to start by setting up your workspace. This means clearing your environment, which we're doing in this first line, setting your working directory, which will change based on where you have your data saved, so your file path won't look the same as mine, and then reading in your data. Here we're using the read.csv function. This CSV is called this. This is the file name, ASNR underscore 2025 underscore abstract underscore data.csv. And we set the header equal to true, meaning that we want it to read in the column names as well. And we set the strings as factors equal to true because anything that's a string, we want it to be read in as a factor and not treated as a string. So this is basically forcing that into a different data type. So we're going to click the play button right here to run it. And now we can see in our environment that we have, if I can get this to drag, we have 598 observations by 116 variables, and it's named DF for data frame. So now we're going to load some packages that we plan to use, which will be Tidyverse and Broom. We'll need these packages for some data cleaning and manipulation that we'll be doing. So we're going to run this. And then, as always, we're going to get familiar with our data. So we can get a glance of our data by using this head function. This will show us the first several rows of the data set and allow us to scroll through to see all the variables. So we're going to hit run. So here, this is an X column. I don't know, it's just random, like it's there. Sometimes when you read in a data frame in R, it'll add this X column. And then we have like visit ID, we have age, we have gender, education, some ethnicity information. We have some other variables going on like white matter, hyperintensities, and other health information. So honestly, this is a lot of data. Like this is just a very quick glimpse, but we have all this data and it's pretty helpful to just get a feel for it before you start doing stuff, especially if it's something that you're not familiar with. So usually what I do is I get rid of the X column because it's unnecessary and annoying, but honestly, to each their own. So for more context, we'll get rid of the X column just to make life easy. So for some context before we get into like the analysis and making the plot, this data set is a cross-sectional, comprehensive data set to look at brain aging and Alzheimer's disease in a diverse sample, particularly Hispanic, Latino, older adults. So we have general cardiovascular markers, like we have blood pressure here. We have some metabolic things like diabetes, along with some MRI and PET data that you can see here to look at amyloid positivity and other proteinopathies present in Alzheimer's disease, along with measures of cognition and daily functioning, which this is why there's something about informant, like what's their ethnicity or race, and then also just further on, there's more information about the informant and then their responses. So this also actually contains some data on motor measures collected in older adults, like gait speed. Interestingly, a lot of research has demonstrated an association between gait speed and Alzheimer's disease pathology, but this relationship hasn't really been explored in Hispanic, Latino, older adults. So for this analysis, we're going to test the extent to which average gait speed is associated with brain amyloid in Hispanic, Latino, older adults. So we can do this with some type of linear model, right? But the type of linear model we use will heavily depend on the distribution of our dependent variable, average gate speed. So we're going to start by doing a visual distribution check of our variable, average gate speed. So when I run that, here's a histogram of average gate speed using the hist function. As you can see, it's a bit skewed. So we're like, it's already tipping us off to be like, maybe we can't do a typical linear regression, right? But let's do a statistical normality check using a Shapiro-Wilk test. So in R, to do a Shapiro-Wilk test, it's shapiro.test, and then you just give it the data frame and the variable that you want to test. And so when we run that, it is definitely statistically significant, meaning that our data is not normally distributed. What can we do then? Our data is not normally distributed. Instead of using a typical linear regression, we can do a robust regression. A robust regression is essentially like linear regression, but it doesn't assume a distribution type and it uses a different estimation method. First, to be able to do this, we need to load the robust regression packages of robust base and robust. Then after this, I'm going to list all of my variables of interest. These are all my predictor variables of interest, and I do this because I, one, need to see them all before I write them in the formula, and two, because I need to make sure that all of my categorical variables are being treated as such. So here I've listed which ones are my categorical variables, and so now I'm going to change all of my categorical variables to factors. So here, this is how it can be done. This is kind of like a long way to do it, but this is the clearest way, is I'm saying for this variable, A beta positivity in this data frame, change it to a factor. That's what asFactor does. So if I run this, it's going to do that for all of these variables mentioned here, like gender, diabetes, blood pressure, and then I have this last line to check the structure, so it should tell me that that was changed to a factor. So if I run it, this last line structure is telling me, yep, it was changed to a factor. So I can assume safely that all of these were changed to factors as well. Now that that's done, we can run our robust regression using the lmrob function. It's formatted like a typical linear regression where we have the dependent variable on the left, then the tilde, and then all of our predictor variables on the right. We also have an interaction term here at the end of ethnicity and diabetes due to the higher rate of diabetes in Hispanic Latino older adults than non-Hispanic white older adults. And then to get the results, oh, and we also have to specify the data frame so R knows where to pull these variables from. Then to get the actual results to print out here, we're using the summary function and LM because that's what we called our robust regression model up here, LM. So we have summary LM to print the results right underneath it. So we're going to run it. Boom! Look at that. Look at that. Look at that. So if you're curious, from this, we can deduce two things. Compared to Hispanic older adults, non-Hispanic white older adults had 0.27 seconds faster gate speed when holding all other variables constant. Then, compared to those without diabetes, those with diabetes on average had 0.32 seconds slower gate speed when holding all other variables constant. So this is cool because we got our results, but now we're going to visualize them with the coefficient forest plot. For the plot, we're going to need to do some data wrangling. So first, we need to get the confidence intervals from the robust regression model. However, they're not inherently calculated like they would be for linear regression. So we're going to use the confint function to get the confidence intervals, and we'll store them in their own variable called CI. Next, we need to convert our model to a standardized clean data frame using the tidy function. We also want to do some other things like adding the low and high confidence intervals to this data frame to get the bars on our plot. Lastly, we'll add a categorical variable that indicates whether a coefficient is significant or not significant so that we can subsequently color code that based on significance later. Within this code chunk, we will also filter out the variable intercept because we don't need to report that on this plot. So we're going to run this chunk of code. And now we have these new data frames showing up in our environment onto the left side. So here we go. We have our newly created data frame, and then we have it the one filtered out without the intercept. Now we can write the code to create the plot. This is going to be a lot, but we're going to go through it slowly. We can do this using the ggplot function and its various layers. We'll have it saved to the variable lm.coefficient.plot. We'll use our data set called model_df_filt that we just created, and then within the aesthetics argument, we have to specify what we want on the x and y axis. So on the x-axis, if we remember, we want the estimate on the x-axis, we want the term or the predictors on the y-axis, and we want the colors to be different based on significance, whether it's significant or not. So that's why we specify color equals sig, because that's the variable we created above. We know we want it to be a dot plot, and so we have to use the geom point to make it a point plot, because we want to show the individual points on the graph. So we have to say geom point. To get the confidence interval bars to show on the plot, we need to add a geom_error bar layer. In this layer, we have to specify that we want an orientation equal to y to have the error bars run horizontally. And within the aesthetics argument, we have to specify what we want the x minimum and x maximum to be for those bars. So we want the minimum to be the lowest part of the confidence interval, and we want the maximum to be the highest part of this confidence interval. This height is just what looked right aesthetically. This is subjective. You can change this if you would like. Next, we use the scale_y_discrete layer to add, and the labs argument to add labels, because we're basically cleaning up all of the variables that show up on the y-axis, because right now they're showing up as they are coded in the data set, but we want them to be nice and clean for the actual plot. So we're changing IMH_diabetes1 to just diabetes, and so on and so forth for gender, high blood pressure, etc., etc. So we do that for all of our predictors. Then we want to add a vertical line to indicate where 0 is. That's where we had that dashed line to show when the confidence interval is crossing 0. This means we can use the geom_v line layer to add it, and we have to specify that we want it to cross the x-intercept at 0, and that we want the line type to be dashed. Then we want to color code our significance. We wanted the significant variables to be red and the non-significant ones to be gray. So within this, we use scale color manual, and we specify that for the significant values, set it to red. For the not significant values, set it to gray. And then lastly, we use the theme and labs arguments to change subtle aesthetic things about the theme. So like how we want the title aligned with everything else, the size of the font, do we want it bold, do we want it normal? And we can do this for each axis title, and we can also specify these elements for the legend. So we're saying here, like for the legend, we want size 10 font and we want it bold, and we also say where we want the legend to be using legend.position. Then within the labs argument, that's saying what do I want the label for the x-axis to be and what do I want the label for the y-axis to be. And then we say what do we want the title to be. The title is very important. You don't want to forget this. So going through that whole thing, this essentially is the entire plot. But just like everything else in R, if you don't specify what you want to happen at the very end, like to show your plot, then it won't show you. So then we write out lm.coefficient.plot to show us our plot. So we're going to scroll up all the way to the top and we're going to click run. And here is our beautiful plot. She's lovely. This is exactly what we wanted. And so then to save your plot, we're going to use ggsave. So within ggsave, you tell it what item you want to save. For us, it's lm.coefficient.plot. You specify the file name, how you want to name it, and then what file type you want to save it as, along with the height, width, and the units of that height and width. And this will write to wherever your working directory is currently set to. So we'll run it. and then we can check in our Finder if it shows up there. So we're going to go look at our Finder. As we can see here, our coefficient plot was successfully written into this folder because our code worked. I hope this tutorial was helpful and it gives you a new way to visualize your regression results for your next presentation.